it's gonna have to move further out from that nucleus up into the region, the volume that we call N equals 4, right? And so because the N equals 3 valence shell is kind of electrically satisfied and closed, this extra electron has to be stored at a higher potential energy level. We say that this guy goes into the, we're going to call it the quote-unquote conduction band, which is another way for saying it's at the N equals 4 level, where it is not held very tightly. We said that when we move from a closed valence shell to another valence shell, the binding becomes less tight. That's another way of saying that the electron exists at a higher potential energy. And so this spare electron goes to the N equals 4 quote-unquote conduction band. So remember, we got a high energy electron stored in that solid. High energy relative to the electrons that are in N equals 3 quote-unquote valence band. Well, because that electron is sitting there because it's not bound very tightly, now this bulk material starts to behave kind of like a metal did. The metals, we had these loosely bound electrons that we could just push from one side to the other, right? And they conducted. Well, now that we've got these phosphorus electrons sitting up here at high energy, those become mobile and can move across the solid. And so if you take silicon doped with phosphorus, you take a battery and stick it at both ends, you're going to get current flow. The other thing that we can do is we can dope the silicon with something that has fewer valence electrons. This is called type doping, positive doping, because we're kind of creating in the bulk solid an absence of electrons. It's not truly a positive charge because the net substance is neutral, but we're gonna draw them as positive charges because we want to demonstrate or kind of communicate that there are empty spaces available for electrons. So you take silicon, dope it with GA. I don't even know what the name of that is. Whatever GA is, it's got 3 valence electrons. Now we start building the same situation that we had over here. So we've got silicon on this position, marker that's running out. Silicon in all these side positions, GA in the middle. GA only had 3 valence electrons, and so it can only form pairs with 3 of these silicons. And over here, this silicon has an electron. It would like to make a bond with that GA, but the GA doesn't have a valence electron to donate to the bond. And so in this region, there's kind of an absence of charge. Imagine what this means in terms of positions available for electrons. In this kind of bonding, we have not filled that N equals 3 subshell. There are still spaces for electrons available in that N equals 3 level. So by shorting the solid of electrons, we create available low energy orbitals. So there's spaces inside that N equals 3 valence shell that could house electrons, but they don't currently house electrons because we didn't supply the material with sufficient electrons to fill them. Write something over here. So this situation, we have high potential energy electrons. Here we've got low potential energy. Same way that doping with phosphorus allows allowed the silicon to be conductive. Doping with gallium will also allow the silicon to be conductive. I'm not exactly sure how to tell you to think of this, but here's a way I think it's fairly safe. You can almost think of these little spots over here in this picture, these little vacancies created by the gallium as being islands that an electron can jump from one to another to another. So if you have this p-doped or this positively doped silicon, I'm going to draw these little positive spots here. Again, the truth is the material is neutrally charged and it does not have a net positive charge. But I'm going to use this language to communicate that there's spaces available for electrons. The electron can jump from one to another, essentially, and migrate across the solid. People also refer to the holes as moving. You can think of the holes as moving. You can think of the negative charges moving. But suffice to say that providing these low potential energy orbitals in the solid gives a place for electrons to dock to as they move from one side of the solid to the other. So, two different kinds of doping, both make what was previously a non-conductive covalent solid turn into a conductive covalent solid. All right? This gets bigger, gets more important. They figured out a while ago that they could take these two differentially doped solids and stick them together. And when they did so, they developed materials that had very special properties. This is a kind of a diode, and diodes are used in electronics all the time. We've looked at light-emitting diodes in our labs, and this type of diode is also used in solid-state photovoltaics. Let me show you what happens. You take N-doped, negatively doped silicon, and you take P-type doped silicon, positively doped silicon. You sandwich the two together. Now we said that these positive spots represent little low potential energy orbitals available to electrons. The negatively drawn, whatever, are high potential energy orbitals occupied by electrons. If you sandwich these two together, some of these high potential energy electrons are going to jump into the low potential energy electron spots in the positively doped material, and you'll get charge motion from the N-doped type to the P-doped type. So some of the negative charges are going to move over. This is going to cause a little bit of excess negative charge to build up here, a little bit of excess positive charge to build up here. Something important to remember, conduction in these solids was dependent on having those either high energy electrons or the low energy slots that electrons can fit into. When we sandwich these two materials together, the extra electrons from here filled up all the available spots over there. And so this region right in here where the charge is transferred becomes non-conductive. It can't conduct electricity anymore because it neither has the high potential energy excited electrons nor the low potential energy spots available over here to jump through. And so this region starts to become relatively non-conductive. And I want you to examine the spatial distribution here. We said that on this side we had high potential energy. We said on this side we had low potential energy. Well, this arrangement is going to start to look like a capacitor. Let's get to a picture of a capacitor. When we have a capacitor, when we take a charge, a capacitor, you stick a battery on a couple plates and it sucks charge all the way over onto one plate and there's a depletion of charge on the other. And you learn in physics that if you take a negative charge and move from the positive side of the capacitor to the negative side of the capacitor, you have to put energy in, right? It's the whole repulsive forces thing. We want to move a negative charge from over here to over here, we got to put energy into it. If we want to take a negative charge and move it from the negative side of the capacitor to the positive side of the capacitor, that is an energy releasing phenomenon because of, I guess, there's attractive forces between the negative charges and the positive charges, there's repulsive forces between the two negative charges. Same thing is happening in these LED, or these diodes. These diodes set up something that looks like a capacitor. We got a high potential energy spot, a low potential energy spot for the electrons, and we can move the electrons back and forth, but not without seeing the kind of concurrent energy transfers. With an LED, what you do is you take one of these diodes and you hook the negative end of a battery up to the negative side of this diode, and you take the positive end of the battery and you put it on the positive side of the diode. Well, that's going to try to force electrons from the negative side over the positive side. In some discussions, you'll hear them talking about moving the holes from the positive side to the negative side. Either way, you get movement of charge in the conduction of electricity. Note that these electrons are jumping from high energy to low energy. And so energy has to be bled off in some fashion. How do you think that energy gets released? Light emitting diodes. Heat, some diodes will release heat, others are going to release light. Relevant to our lab is that the ones that release light, that difference in potential energy between high potential and low potential is let off in the form of photons. And so these diodes are the ways that they construct light emitting diodes. You force the negative charge from the high potential energy side to the low potential energy side, and you get photons releasing that energy. Okay? Solid state photovoltaics. Same exact system, now we're operating it in the reverse direction. Again, we've got sandwiched N-type and P-type semiconductors. We've got this kind of non-conductive region in between. And now what we're going to do is we're going to let photons come hit this positive type material. When they do so, that photon energy is going to be absorbed by the electron. The electron is going to get promoted to high energy. It jumps over off onto this negative side. So when the light energy is absorbed, the electron goes from low potential to high potential. And because this area in here is not very conductive, it's got all of its carriers, its charge carriers are kind of depleted. The electron is forced to take the long road home. So you provide it with a conductive path to get across, and this becomes your battery. So PN junctions used in solid-state photovoltaics, used in light-emitting diodes, simply provide low energy and high energy positions for the electrons to exist at. And in the light-emitting diode, the electrons go from high energy to low energy. In the solid-state photovoltaics, the photon gets absorbed and promotes the electron from low energy to high energy. Questions? Has this been confusing, or has this been fairly easy to understand? I'll never know. Yes?
How does those electrons pass from the positive side to the
To talk about this, we're going to have to start talking about like tunneling. Have you guys heard of tunneling? So when you're a wave, you have some probability to be places where you're not. You can jump from one space to another. There's something going on with that where when the photon hits the electron, it gets excited and it jumps this gap, but its waveform kind of crosses that gap, but it can't get back across that gap as readily or very easily as it. When the photon hit it and excited it, it was able to jump the gap. But now that it's trapped over here, it can't get back across that gap without the photon energy, and so it has to go the long way home, and you get a current loop. Okay, so that's the solid state devices. Today in lab, we're going to be looking at the dye-sensitized solar cells. Those are the photovoltaics that mimic biological systems. I talked about them in class already for a minute. We'll just do it one more time real quick, if I can find the slides. You guys want to hear something awesome?
Yeah.
Got home and a water line in my truck was leaking. And so I went in and I got to work on my damn truck. I'm in there and I got a screwdriver and I'm trying to tear apart this thing called a Ford Quick Connect, which does not connect quickly. It's called a quick disconnect. It does not disconnect quickly either. You have to take it apart with a hacksaw in my experience. Anyway, I'm in there and I'm juggling around and I've got a screwdriver in my hand and I'm looking over here at something while messing with the screwdriver. And the screwdriver flips out of my hand and disappears into oblivion, into the ether. I don't know if like little trolls came in and stole my screwdriver or if it went into like the fourth dimension within my engine compartment, but I now officially have a missing screwdriver in my engine compartment, which scares the living shit out of me. Oh no, is it gonna turn off on me? I hate Windows. Right in the middle of class. Dye-sensitized cells. So, we talked about photo excitation of these things, of electrons. And we said that once the electron becomes photo excited, it is able to be pulled on by other things. So when the electron's tight and bound tightly to the nucleus, it's held very strongly by the nuclear charge. You throw a photon at the thing, you promote it to some excited state, now it is no longer attached tightly to its nucleus, and some other species might, if it has a chance to, get a hold of that electron and pull it over into its own nuclear charge. So, in the dye-sensitized cells, which were kind of built on the same kinds of systems that are responsible for photosynthesis and the citric acid cycle. The citric acid cycle is like photosynthesis, it's just electron transfer. What you have are these ground state electrons that are low energy. You hit them with a photon, and they get promoted to some high energy state. You can think of this in terms of the hydrogen atom, maybe you're going from n equals 2 to n equals 6 or something like that. But you're pumping that guy up, you got high energy. Now there was something else here, some other species, that has an orbital available for that electron that is lower in energy than the excited state, but higher in energy than the ground state. This species, whatever it is, maybe it's some positive charge sitting out in space, was not able to pull that electron when it was in the ground state. But once that electron gets promoted to the excited state, now this guy can exert enough force on it to pull the electron over into its own realm. And so the electron will jump, boom, from here to here. Oftentimes in these systems, you've got multiple carriers. So you stick another kind of low potential energy carrier over here somewhere, the electron might be able to move from this guy off to this guy. But suffice to say, if you provide a path for the electron to get back to the ground state, then what you've generated here is a photo-induced cyclic charge path, right? Current loop. Now you've got electrons traveling in a cyclic pattern. You can harness that for power. This is the way that the energy of the excitation state gets dissipated as the electron flows downhill in energy. Biological systems use these different stages to construct biomolecules that harness that energy, store that energy, and get used downstream. Your dye-sensitized cells, draw this real quick. You've got the following. 2 pieces of conductive glass. Incidentally, glass is not normally conductive. Glass is made of silicon, right? Silicon's not conductive. They treat this glass with a very thin film that is conductive. That thin film ends up being a tin oxide or a titanium oxide or something like that. But suffice to say that that treated side of the glass slide is able to conduct electricity. Now on one of these slides, they've got a mesh, a lattice of solid titanium dioxide. It's a white powder. Within that white powder, they've distributed a bunch of chromophore molecules. The chromophore molecules represent the ground state home of the electron. Chromophore molecules, we'll find out, are often these conjugated molecular systems. Turns out conjugated molecular systems are able to provide orbitals at higher potential energy for these electrons, but low enough potential energy that the electron can actually transfer the gap between energy levels. So this titanium dioxide powder is just littered, I'm going to draw little dots, it's just littered with these chromophore molecules. In here, between the titanium dioxide and the other slide, is a solvent. That solvent happens to solubilize I2 and I3 minus. These species are soluble in this solvent, and so they're distributed evenly throughout the solvent, and they can move about within it. Here's what happens. You hit this chromophore with a photon. You promote an electron into the excited state of the chromophore. The excited state of the chromophore is this guy. I'll call this E1. The problem is that chromophore is sitting right on top of solid state titanium dioxide. Titanium dioxide has orbitals available in it that are lower in energy than the excited state, but higher in energy than the chromophore itself. And so that electron gets pulled off into the titanium dioxide. It goes downhill in energy, now it lands on the titanium dioxide. The titanium dioxide is in contact with this conductive glass. And so the conductive glass grabs a hold, pulls the electron from the titanium dioxide, and it shuttles it all the way around to this piece of conductive glass. Now this electron is sitting here on this side, and it's in contact with this solvent, which houses these I2, I3 minus species. I2, I3 minus, if you take an I2 and you take two I2s and you throw an electron at them, one of the I2s will break apart, it'll grab that electron and it'll join with another I2 and get an I3 minus. That I3 minus ion now kind of contains that electric charge. So the electron has moved downhill in potential. It's landed on the I2, it's become I3 minus. And the I3 minus moves across the solution and gives that electron back into the chromophore. So you've got a cyclic path for that electron. You can throw another photon at it, it'll go through the same path again. Throw another photon at it, it'll go through the same path again. Those are the biological photovoltaic systems. They only discovered this stuff about 10, 15 years ago. It was big news in science. The guy that figured out a way to engineer these systems got a Nobel Prize, and they believe that this is the technology that's going to revolutionize the way we do solar panels. It's going to take years and years of development. We've been doing solid state things, 20, 30 years, 40 years, something like that. We've just begun this stuff. But as they get better at this technology, it will hopefully replace solid state devices. Does anybody know what some of the problems with solid state devices are? The current solar panels that we use?
That they use platinum or
What's okay, so you're getting towards the point I wanted to make. The dopants that they use for these materials, regular silicon, there's a shitload of it. You go out to the beach, there's silicon all day long. We got tons of silicon on planet Earth. It's one of the most abundant atoms that we've got. But the dopant species that we're using currently for these solid state devices are rare earth metals, a lot of them. A lot of rare earth metals, rare in general. We don't have enough of them to make solar panels for the whole planet. Plus, it costs an arm and a leg to mine them. You gotta dig them up out of the ground. There's environmental costs for having to dig them up out of the ground. There's the fact that we've got limited resources in terms of those. Solid state devices are not necessarily a good idea for the long term. They're working right now. They're energetically costly. Don't quote me on this. I was in a coffee shop 20 years ago, 15 years ago, and I was surrounded by a bunch of engineers. And one of the engineers was saying, well, if you take the net carbon footprint for making one of the solar panels, again, you gotta go mine the stuff, you gotta purify it, you gotta build it, you gotta ship it across seas, etc. At the end of the day, this guy was saying that it costs more in energy to make the solar panel than that solar panel actually made in its lifetime. Not a good trade. I mean, I'm sure that over the years, those margins have changed, and it becomes more energetically efficient to make them. But suffice to say, it still costs a lot to make these solid state devices, and we're making them out of materials that are rare and problematic if they're leached out in the environment. So the world is really hoping that these systems that mimic biological systems will end up taking over, and hopefully they do. All right, that's today. Real quick, lecture on Thursday. Nothing new, just review and working with the material that we've already shown you. So the stuff that you've seen up until now is the stuff you'll be tested on. And